Scattering matrices for semi-analytical methods. In this lecture, we'll discuss some preliminary topics like the definition of a scattering matrix. We'll then move on to formulating the equations to calculate a general scattering matrix. We'll then derive what I call the improved scattering matrix. We'll talk about that a little bit and then describe how to use these scattering matrices to simulate structures that are composed of multiple layers. Preliminary topics. What is a scattering matrix? Well, a scattering matrix comes from network theory, and it essentially relates inputs to outputs. So here we're drawing a layer of our device, but in terms of network theory, this is a black box, and we don't want to care what's inside of it. We would just like to characterize it with a minimum set of numbers. And so in the context of scattering matrices, that is 4 numbers. And we're relating inputs to outputs. So what are the inputs here? Well, on the left-hand side, port 1, a port is just a place where we can have inputs and outputs. So the inputs into port 1 is the C1 plus, the plus meaning it's a forward propagating wave, the subscript 1 meaning it's going into port 1. So C1 plus is an input. We can also look at port 2, and C2 minus is an input from the right. The C1 plus, the input from the left. So here are our inputs. We then, if we pre-multiply that by our scattering matrix, we get our outputs. Well, what are the outputs? We can have a reflected wave on the left, or we can have a transmitted wave on the right. Let's talk a little bit more about the scattering matrix elements themselves because they have physical meaning. If we have an input into port 1, a little bit of that could get reflected, or a lot of that. How much gets reflected is described by the S11 parameter. So S11, in fact, is the reflection coefficient from port 1 of this device. And it is so commonly understood this way that very often experimentalists will just use the word S11 synonymously with reflection. Hey, what's your S11? So expect that when you talk to people or read the literature. Likewise, S21 is characterizing how much of the wave coming in from the left exits from the right. That is a transmission coefficient and often used synonymously for transmission. Hey, what's your S21? So S11 and S21 are the more common scattering parameters to be discussed. And that's really because S22 is the same thing as S11, just from the other way. We're talking about reflection from port 2. The S12 is how much of the wave entering port 2 exits port 1. So that is a backward transmission coefficient, if you will. And we would expect in linear reciprocal media that your S11 and S22 are actually equal, and the S21 and S12 are also equal. And in fact, that is the case. So that is the scattering matrix, and that's what we'll be using here. Why do we want to use scattering matrices? Well, first, it's an unconditionally stable method. What that means is, as long as you don't make a mistake in your code, everything's going to work. This will not explode. And we saw previously that transfer matrices, that's not the case. That does explode. And we really didn't even cover how to fix that. The other thing is that the parameters have physical meaning. We know S11 is a reflection, S21 is a transmission, S22 is the backward reflection, a reflection from port 2. S12 is a backward transmission. If we measure things in the lab, well, typically we measure things with a network analyzer or a vector network analyzer, and those are reporting our scattering parameters. So what we calculate in our simulations can match what our measurement equipment is doing. We can also extract dispersion. So for example, if we look at our S21 parameter, we can figure out how much phase is being accumulated through that layer. We can then back calculate effective medium properties and things like that. Scattering matrices are very memory efficient. We can calculate a scattering matrix of one layer, calculate a scattering matrix of the next layer, combine those, and then discard and throw out the information from the first scattering matrix. Move on to the third, throw out the second. And so we really only have to have 1 or 2 scattering matrices in memory at any one time. Other methods for connecting multiple layers, very often we have to retain parameters for each layer as we go. If we have a lot of layers, we can run out of memory. With scattering matrices, there's some really neat ways to simulate periodic devices, things that are periodic in the longitudinal direction. So suppose you have layer 1, layer 2, 1, 2, 1, 2, 1, 2, and that repeats a million times. How on earth do you simulate something like that? There's some really cool ways to do that with scattering matrices very efficiently. Scattering matrices are very well known, very mature. There's a huge wealth of literature available for them. So they're really wonderful for running simulations and doing what we're doing. But I do want to mention, as much as I like scattering matrices, there are also other wonderful methods out there, and we'll cover that in a later lecture. One drawback of scattering matrices, for example, is that they're pretty slow compared to the other methods. Now, for transfer matrix method, you're not going to feel that pain so much because it's so fast anyway. But in other methods like method of lines, rigorous coupled wave analysis, they will slow us down, and using other things can be much faster. For example, in my experience, there's another technique called the enhanced transmittance matrix approach. My experience is that's about 10 times faster than scattering matrices, but at the cost of memory efficiency, the intermediate parameters are more abstract, so it's a little bit more confusing to learn, and they don't have physical meaning. So scattering matrices are not the best, but I do like them for all of these reasons. This is a warning. If you read the literature on scattering matrices where it relates to semi-analytical methods, so this is things like transfer matrix method, rigorous coupled wave analysis, method of lines, and some other things, the scattering matrices used throughout the literature are almost always, I want to say that they're wrong, but mathematically they work. They get the right simulation results. It's just that they do silly things. For example, they will scramble the definition of the scattering parameters, which violates what we know from network theory. So for example, very often in the literature, your S12 is characterizing reflection. That's crazy. That should be a backward transmission. Why even have those subscripts 1, 2, 1, 1, 2, 2 if they don't have any meaning anymore? So this caused me a lot of confusion when I was learning that. Another thing that's done in the literature a lot is asymmetric scattering matrices. So over here in the lower left, we're looking at a layer, and the scattering matrices will relate mode coefficients on the previous layer to the mode coefficients inside the current layer. Now notice this is inherently asymmetric. To make it symmetric, we'd have to be relating mode coefficients on the outside on the left to mode coefficients outside on the right. That would be symmetric. The fact that that's not symmetric means all 4 scattering parameters will in general be different. So we always have to calculate 4 of them and store 4 of them. Whereas there's some neat things we'll do to make this symmetric so that we only have to calculate and store 2 scattering parameters. So that's twice the speed and half the memory requirements. Let's go ahead and formulate the general scattering matrices. Here is the geometry and the basic setup of how we will look at a layer to calculate the scattering matrix associated with this layer. So it's just some arbitrary layer I. On its left is some medium 1, and this could be what's in the previous layer or something else. It is just, at this point, an infinite half space going way off to the left. Medium 2 is another infinite half space going way off to the right. And medium 1 and medium 2 in general can be different, and so we're thinking of them as being different here. Well, the ith layer has a thickness L sub I. The mode coefficients here are describing the amplitudes of the modes, or how much power is in them. Of course, the I superscript is telling us which layer we're in. The plus and minus superscripts is telling us whether we're talking about the forward wave or the backward wave. Now, when we talk about the fields, in the framework of scattering matrices, we're differentiating or separating forward and backward waves. This is different than what we did for transfer matrices. So we'll do really the same thing twice, once for forward waves, once for backward waves. At the top, I'm showing the forward wave. And so this psi, remember, is a column vector that has Ex, Ey, Hx, and Hy. The I subscript is which layer we're talking about. The superscript is whether that's a forward or backward wave. So we're talking about a forward wave at this point. And Z sub I prime, the prime is telling us this is a normalized Z coordinate, and this is our local Z coordinate. that starts at 0 and goes all the way up to k0 times L sub I. And why times k0? Because remember, it's a normalized z coordinate. So we multiply by k0 to normalize our coordinate. So at the very beginning of the layer, at local coordinate z equals 0, this is how we would write our fields, c sub I at z equals 0. At the far right-hand side, after the wave has propagated all the way across this layer, we write that as psi sub I of k0 times Li, our normalized z coordinate. And the exact same thing really for the backward wave. The only difference is we're writing with a minus superscript to remind us that is the backward wave. So at the very beginning of the layer is psi sub I with the minus superscript at local coordinate z equals 0. And at the far right-hand side, psi sub I with the minus superscript at k0 Li. Very quickly, in the medium 1, just to the left of layer I, we have at this first point exactly psi 1 plus. We're not writing this as any kind of function of z because in the context here, we don't really care what happens or what it looks like moving away from the interface. So we really just have the fields immediately at the interface. And we have that for the forward wave and the backward wave. We have our mode coefficients for this medium 1. We have our mode coefficients for this medium 2. And likewise, the size here representing the fields are the fields immediately at the interface. We're not writing them as a function of z because we really don't care what they look like as we work away. We just care what the external fields are immediately at the interface. So this is the geometry that we will proceed with for our formulation. The first step to derive our scattering matrices is to enforce the boundary conditions at either side of layer I. So we have two interfaces. So let's remember how we're writing the field inside the I layer. So we've been writing that as psi sub I, and remember it has an EX, an EY, an HX, and an HY components, and each of those are changing as a function of the local coordinate z. Our overall solution is written as a combination of our eigenvector matrices, our eigenvalue exponential matrices, and our mode coefficients that are describing the amplitudes of the modes. So let's look at the first interface. We are essentially setting these two psi's equal to each other. So whatever the psi is in layer 1, we have to set that equal to whatever the psi is in layer I at z equals 0. So in terms of how we're writing our fields, this is how we express both of them. Now remember, the psi sub I in medium 1, we're only ever caring about the fields immediately at the interface. So there really is no z dependence. So in a way, we can think of the local z coordinate in medium 1 as being 0 right at the interface and going negative as we work left if we needed them, but we don't. So with z equals 0 right at the interface, the exponential matrix becomes the identity matrix, and it really just drops. So we just have our eigenvector matrices of that medium 1 and the mode coefficients for medium 1. Then over in layer I, we're still at local z coordinate equal to 0, but we're inside layer I now. Since local z equals 0, this exponential matrix goes to the identity matrix, and we just end up with the eigenvector matrices in layer I multiplying the mode coefficients in layer I. So that's a pretty simple equation for the boundary conditions at the first interface. Let's look at the second interface. So we are setting the psi's equal that are inside layer I, right at the second interface, that's at local z coordinate k0 times Li, to the fields in medium 2 immediately at the interface, that's psi sub 2. Now, in layer I, since our local z coordinate is not 0, well, now we have this exponential of the eigenvalue matrices. We still have our eigenvector matrices of layer I. We still have our mode coefficients of layer I. Then in medium 2, we don't have this exponential matrix because the local z coordinate is 0, and that becomes the identity matrix, but we do have the eigenvector matrices in medium 2 and the mode coefficients in medium 2. So these two equations are enforcing the boundary conditions at either of the interface. And it's really from those two equations that we derive the scattering matrices. Here, I'm just going to present the outline of how we derive the expressions to calculate the scattering matrix. The details of the derivation is reserved for a homework assignment. So what we have are the equations from the previous slide where I've solved both for the mode coefficients in layer I. So we have the mode coefficients equals a bunch of stuff, and this comes from our matching the boundary conditions at the first interface. And then we have the C sub I mode coefficients equals a bunch of stuff, and this came from matching boundary conditions at the second interface. Now at this point, notice both of these expressions have a somewhat complicated matrix division going on. We have the eigenvector matrices for medium 1 being pre-divided by the eigenvector matrices of layer I. And a similar thing's happening over here, except we have the layer 2 eigenvector matrices. So the next step is to handle that. And it turns out we can simplify that matrix division this way, where we're calculating these A's and B's from the various eigenvector matrices. And the subscript J is either going to be 1 or 2, depending which case we're talking about on the top. But since they both look the same in general, we could just substitute in a J subscript and do both at the same time. So now what we'll do is we'll take this simplification and plug it into these top two equations to simplify them. Then also notice both of these expressions are simply the mode coefficients. So we can set this expression equal to this expression, of course, having substituted in our simplification that we just derived. And we end up here. So we've eliminated those mode coefficients C sub I. We have now only an equation with the mode coefficients for medium 1 and medium 2. So at this point, we have a 2 by 2 block matrix equation. We can actually expand that to two separate matrix equations. We'll take those two separate matrix equations, rearrange all the terms so that it's in the form of a scattering matrix. And however the terms collect here will be our final scattering matrix. And that's what we'll show on the next slide. So if we do all that, here's where we are. And here's how we would calculate our four scattering matrix terms. Now, before I had hinted that S11 and S22 should be equal, and S12 and S21 should be equal, and here they're clearly not. And we might ask why. Well, that's because we have an asymmetric case. In general, medium 1 and medium 2 can be different. So at this point, we're forced to have to calculate all four scattering matrix parameters and store all of them. So that's the formulation of the general scattering matrix. Now there's a limitation. Notice we have a layer I surrounded by medium 1 and medium 2, and it makes sense that the scattering around layer 1 would depend on what medium 1 and medium 2 is, of course. Well, here's a problem. Let's say we would like to simulate transmission and reflection through this stack of 20 layers. And if we look at this long enough, we'll realize there's actually only 3 unique layers. I would like to only have to calculate 3 scattering matrices and just reuse them and multiply them or combine them however we do that in a way that we can then calculate the scattering matrix, the overall scattering matrix for the 20 layers. However, since the scattering matrix for layer I depends what's on the outside, if I come down here to, for example, this orange layer, it's got a green striped layer on its left and a blue checkered layer to its right. That would have some scattering matrix. Over here, we have an orange layer to the left and a blue checker to the right. This would be an entirely different scattering matrix. So we can't just calculate 3 scattering matrices and reuse them. We're forced to have to calculate 20 separate scattering matrices. And this is a fundamental limitation of this. There's a clever fix for this. So let's talk about that, the formulation of an improved scattering matrix. So let's just get the concept of what's going on here. So here's our stack of 20 layers again, and we only have 3 unique layers, but we realize that all 20 layers are going to have their own unique scattering matrix, which makes it so that we can't just calculate 3 unique scattering matrices. Well, what if we separated all of those layers by some gap? If we can do this, now each of those layers is surrounded by the same medium. We will call that the gap medium. This makes it so that if we calculate just 3 scattering matrices for our 3 unique layers, we can just simply reuse those and combine them. We don't have to recalculate new scattering matrices. However, if we introduce gaps, don't we change the electromagnetic problem? We would, except we're going to let the thickness of those tiny gaps be 0. So if the gap thickness is 0, it has no electromagnetic effect, but it does have a profound mathematical effect in that we can interchange all of our scattering matrices however we want to. We don't have to care what scattering matrices are connected on the left and the right. They all work because they're all surrounded by the same scattering matrix. Another cool thing happens. These now also become symmetric, right? Because it's surrounded by the same medium on each side. That means our S11 will be equal to S12. Our S21 will be equal to S12. We only have to calculate 2 of them. We only have to store 2 of them. So it's faster, simpler, more memory efficient. We can interchange however we want to. It's just better all the way around. So I think this is the proper way to do scattering matrices. So let's remember how we set up our general problem. So we only have a simple change if we want to change this over to our new and improved scattering matrices. We simply replace medium 1 and medium 2 with the same gap medium. It's important to note that this is the same medium on either side. That's what gives it its symmetry. Otherwise, it's really the same setup as we had before, but with this symmetry. So here's how we would calculate the scattering matrix element for these improved or revised scattering matrices. We didn't have to do another derivation. We did all of our work for that general case. This is a special case of that general case where medium 1 and medium 2 are the same medium, and we'll call it this gap medium. And the gap medium doesn't have to be any medium that appears in the simulation anywhere. It's just something that we're free to choose. Usually we'll just choose free space. Sometimes you'll see that there's a better decision to make for that, but in general, we can choose whatever we want to. So now our S11 is equal to S22, and S12 is equal to S21. So we only have to calculate and store 2 scattering parameters. Our scattering matrices are symmetric, there's fewer calculations, less memory storage, and we've simplified everything. Let's just talk about these scattering matrices for a little bit. One thing that comes up, and it's not critical this is completely understood, but we've been thinking about our layer as a 2-port network, port 1 on the left, port 2 on the right. But when we calculate these things, a lot of students notice that these scattering parameters, each and of themselves, are 2 by 2 matrices, and they become curious why our scattering matrix is actually a 4 by 4 set of numbers. Well, it turns out that we actually have a 4-port network. And this is how it works. We have what we were calling port 1 actually has 2 ports because remember there's 2 possible electromagnetic modes, and each one of those can have a forward and a backward wave. So we have 2 modes on the left, 2 modes on the right. Each of those can have an input and output. That's a total of 4. So we actually have a 4-port network. But because we've lumped all these things into block matrices, we tend to think of this more loosely as a 2-port network, but that's not quite accurate. Don't worry too much about understanding this. It comes up a lot, and I wanted to point that out. If we are calculating the scattering matrix that is symmetric, it's the same on both sides, and it has lossless media, so no loss, no gain, our scattering matrices are unitary. And what that sort of means is it's conserving the amount of power. And so unitary matrices have some properties. So here we have what's called a Hermitian operation or a complex transpose. What this is we take the transpose of the scattering matrix, and then we also take the complex conjugate of all of its elements. If doing that is the same thing as the inverse of the matrix, then we have a unitary matrix. And so, we can write a bunch of properties for this. So we don't have to use this in our code, but we can use this to troubleshoot. If things aren't working, one thing you can do is go check and make sure that your scattering matrices are unitary. If they're not, that's a hint about what is going wrong. Even if you're simulating something with loss or gain or that isn't symmetric, you can go in and turn off the loss, turn off the gain. Check if your scattering matrices are unitary. If they're not, something's wrong. Once they are, then you can turn the loss and the gain and other things back on. So it's a great check, but it's not really something we need to know to implement the codes. I will also mention, in the general case of the asymmetric scattering matrices, those are not unitary. We have to have the same medium on either side for them to be unitary. Now, if you go ahead and derive the expressions for the scattering matrices on your own, what you'll discover is there's actually lots of algebraic ways to do this, and you can come up with expressions that are simpler than mine. The problem is, a lot of them don't work. And when I was first going through this, I was extremely confused, and I didn't know what I was doing at the time. But in hindsight, here's what was going wrong. If we look at our scattering matrix, the S11 and S21 tend to be the larger numbers. So if we have to divide by something along your diagonal rather than the off diagonal. Also remember this matrix X, that's describing propagation through the layer. That's the exponential of the eigenvalue matrix. We don't ever want to divide by that. And there are some formulations for scattering matrices where we are dividing by, but those are unstable. So we want a formulation that never divides by that X. So these were the two big things I was missing when I was formulating scattering matrices. Last thing we're going to talk about is how to handle multi-layer structures. How do we combine adjacent scattering matrices into one sort of overall global scattering matrix? So a bit like the transfer matrix method, we're going to look at our simulation as a stack of layers. Each layer has a scattering matrix associated with it, and we will somehow combine those. Now, this is not matrix multiplication. That was for transfer matrices. This is something different. It is not matrix multiplication, so don't do that. It's something called the Redheffer Star Product. Let's go ahead and derive how we would combine two scattering matrices. So let's say we have two adjacent layers, A and B. Well, we have a scattering matrix equation for layer A scattering matrix equation for layer B. The first thing to do is to separate both of those 2x2 block matrix equations into the two matrix equations that they're representing. So our first 2x2 block matrix equations becomes these two matrix equations. And our second 2x2 block matrix equation becomes these. Now we'll focus our attention on equations 1 and 2. Remember, our overall goal here, we would like one scattering matrix equation that does not contain any C sub 2's. So if we look at equations 2 and 3, each of these contain C2 plus and C2 minus. But if I substitute equation 2 into equation 3, I can eliminate C2 plus and have an equation that only has C2 minus. Likewise, I can substitute equation 3 into equation 2 to eliminate C2 minus and get an equation that only has C2 plus. So I've done that, and here's the two equations that we have. Now we can take those two equations, substitute them into the two equations we have not used yet, equations 1 and 4, and we can completely eliminate C2 minus and C2 plus. Now we have two equations that don't contain C2 at all, only contains the C1 minus, C1 plus, C3 minus, and C3 plus, and we can rearrange the order of those equations such that we can collect them into one 2x2 matrix equation that has the form of our combined scattering matrix. And the details of this are reserved for the homework. So when we're done, we can write our Redheffer Star product this way. We will have two scattering matrices. We would like to combine them into one overall scattering matrix that's describing propagation through the combination of two layers. And from the previous slide, this is the result that we would get to do that. So this is called the Redheffer Star product. Clearly, this is not matrix multiplication, so don't do that. That would be wrong. It's a Redheffer Star product. So let's put this all together and figure out how we're doing things. One issue that will complicate this a little bit is this gap medium. That may not be the medium that our device is actually floating around in. And so we have to think about that. Okay, so let's say we want to simulate transmission reflection through some complicated device, and it has a bunch of different layers. So we will look at layer 1, and we will calculate its scattering matrix. We will then initialize what we call the device scattering matrix with that first scattering matrix we just calculated. Once we do that, we can discard this scattering matrix. We will then calculate the scattering matrix for the second layer. And then using a star product, we can update that device scattering matrix. Now we can discard that second scattering matrix. We can calculate the scattering matrix of the third layer. Do the Redheffer Star product and update our device scattering matrix. And we do this through our entire device. So let's say that there's n layers through this device. At this point, we have what we call the device scattering matrix. However, this is our device lying in our gap medium, which may not be the actual medium that the device is residing in. So what we need to do is connect that device scattering matrix to the outside world, whatever that might happen to be. So we'll come up with what we call connection scattering matrices. So we will have a scattering matrix that'll have the gap medium on the right, whatever medium is actually in the reflection medium, maybe this is just air or something, and we will give this layer a thickness of 0 so that it has no electromagnetic effect, but it does connect our device to whatever happens to be on the outside world. So we add this star product with our connection scattering matrix, or we'll call it the reflection side scattering matrix. We have our transmission side, whatever medium might happen to be over here. We'll give this layer 0 thickness, and then we do another star product to connect our device scattering matrix to the outside world. So once we connect our device scattering matrix to the outside world, we call that the overall global scattering matrix. And that's the final one that we will calculate transmission and reflection from. So if we go back to our general scattering matrix derivation, we'll realize again, this is a special case of that. Here we have different mediums on either side, so our scattering matrices are not symmetric, and we're forced to have to calculate 4 different parameters. But we are giving this gap medium a thickness of 0, so that X in here became the identity matrix. And our equations simplify considerably, but these still are the equations from that general scattering matrix, just simplified for this reflection side. And we can do the same thing for the transmission side scattering matrix. So here's a summary of everything. The first thing we'll do is we'll step through the device, however many layers that would be. That's our device scattering matrix. Problem here is now we have our device residing in whatever gap medium we chose, which may not be the actual medium that's outside the device. Now, if it was, we're done. The global scattering matrix and device scattering matrix are the same thing, so maybe that's a convenient choice for you. But there's time for maybe we don't want to do that. In which case, we have to include this reflection side scattering matrix, the transmission side scattering matrix, to connect it to the outside world. When we do that, we get our global scattering matrix. And now we're ready to finish the problem, which is something we need to talk about in a later lecture.
From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.